Welcome to AI Paper Slop. Today, we are looking at a brand new release called OPSD. That stands for Self-Referenced On-Policy Self-Distillation, and it's by Zuo Sun and colleagues.
It's a really fascinating one, too.
Yeah, and for the technical folks listening, here is the 60-second download, no fluff. On-Policy Self-Distillation, or OPSD, is this incredibly powerful tool for giving large language models dense, token-level feedback.
Right, which is great in theory.
Great in theory, but in practice, it has a fatal flaw. I mean, the teacher model is a moving target that co-evolves with the student.
And that just causes massive optimization instability.
Exactly. It leads to a phenomenon known as rule collapse. So SROPSD solves this mathematically by completely separating where the target is placed from how the student is projected toward it.
It's a really elegant fix.
It is. It anchors the target using a frozen reference policy and then projects the student towards it using a tunable metric called Rényi divergence. The result is, well, state-of-the-art stability and performance across science, hardcore math, and coding benchmarks.
And it does all that without destroying the model's base capabilities.
Which is the holy grail.
Yeah.
So to really understand why this is a breakthrough, we need to look at the daily reality of an ML engineer trying to improve an LLM's reasoning.
Right, because if you are fine-tuning a model for math or code today, you are likely relying on algorithms like PPO, DPO, or GRPO.
Basically reinforcement learning with verifiable rewards or RLVR methods.
Exactly. You give the model a coding problem, it writes a script, you run a unit test. If it passes, it gets a reward. If it fails, it gets penalized.
That makes intuitive sense because it's completely verifiable, right? We don't need human annotators to tell us if a Python script compiled successfully.
It is verifiable, but it suffers from a devastating sparsity problem. I mean, those algorithms rely on sequence-level rewards.
Which means what exactly for the training process?
Well, a model might generate 2,000 tokens of highly complex logic, and then it makes a tiny arithmetic error at token number 40.
Oh, and that cascades and causes the final unit test to fail.
Exactly. The algorithm then slaps a single negative scalar penalty on the entire 2,000 token response. The model has absolutely no idea which specific token or reasoning step actually caused the failure.
It's like grading a 10-page calculus exam with just a giant red fail stamp.
Right. Instead of circling the exact line where the student forgot to carry the one.
So the model knows it did something wrong, but the credit assignment is so sparse that it struggles to learn how to fix it.
That is exactly why researchers started looking so closely at on-policy distillation, or OPD. It attacks the sparsity problem directly.
Because instead of a single sequence-level reward, OPD uses a teacher policy, right?
Yes, to provide dense token-by-token supervision on the exact trajectories generated by the student itself.
So at every single step, the teacher provides a target probability distribution.
Right, which completely eliminates the state distribution mismatch that plagues offline distillation. You know, where a model is forced to learn from trajectories it would naturally never generate.
But there is a catch with standard OPD.
Huge catch. Standard OPD requires an external oracle teacher, like GPT-4.
Which is computationally expensive, proprietary, and, well, often just impractical for continuous training.
Exactly. So researchers moved to on-policy self-distillation.
You don't call an external API, you use the model itself.
Right, you create a self-teacher. And that is typically an exponential moving average, or EMA, copy of the student model.
But how does the self-teacher know more than the student if they're basically the same?
To make this self-teacher capable of actually teaching, you feed it privileged information during the forward pass.
So you condition it on verified ground truth solutions or something?
Yeah, or environment feedback, or successful reflections. The self-teacher uses that extra context to generate a rich token-level target distribution for the student.
And the student doesn't have that privileged context.
Right, so the student is forced to learn from the teacher's richer representation.
So for the ML engineers listening, think of the optimization process like trying to train a robot to navigate a maze by having it chase a laser pointer.
Okay, I like this analogy.
Right. In self-distillation, the laser pointer isn't being held by a human standing outside the maze. The laser pointer is mounted on the robot's own arm.
And that leads us to the trap of the moving target. It's the core bottleneck of current self-distillation.
Because everything is moving at once.
Exactly. The target you are trying to hit, the context distribution, and the policy you are optimizing are all intrinsically coupled. They're changing simultaneously.
And when you try to match this moving target using standard math-like standard divergence metrics, the optimization just breaks down.
It completely breaks. Let's
Yeah.
look at forward KL divergence first. Mathematically, forward KL takes the expectation over the teacher's distribution.
But during on-policy training, you are sampling tokens from the student's distribution.
Right. So you have a fundamental action level expectation mismatch.
You're evaluating gradients on paths the student took, but the math is expecting paths the teacher would take.
Exactly. To visualize this, think of mode covering. That's what forward KL tries to do. It's like trying to stretch a giant elastic blanket over an entire mountain range.
Okay, so the teacher's distribution represents all the peaks.
Yeah. And the blanket tries to cover every single peak. But because of the sampling mismatch, the blanket ends up loose, inaccurate, and often hovering over empty valleys.
It overestimates the probabilities of bad tokens.
Yes, leading to wild instability. And because of this, many researchers shift to reverse KL divergence.
Which takes the expectation over the student's distribution.
Right. Which perfectly aligns with how we sample tokens during training.
But reverse KL brings its own poison, right? Which is mode-seeking behavior.
Exactly. If forward KL is a blanket trying to cover the whole mountain range, reverse KL is like dropping a very tight, highly accurate tent over just the single highest peak.
It's incredibly precise for that one spot, but it completely ignores the rest of the mountain range.
It weakly corrects modes that are underrepresented by the student. So because the laser pointer is mounted on the robot's own arm, as the self-teacher co-evolves with the student.
So tech's amplifying the model's own existing biases.
Exactly. The model finds one reasoning path that works slightly well, and reverse KL forces it to aggressively collapse all probability mass onto that one path.
So you get a catastrophic loss of output diversity.
The entropy of the policy collapses, and the model literally forgets how to reason in any other way.
The robot stares at its own laser pointer, amplifies its own navigational error, and spins itself right into a corner.
That is exactly what happens.
So we need a way to unmount the laser pointer from the arm. And this brings us to the first structural fix in the paper.
Right, OPSD, self-reference on policy self-distillation.
The authors start by completely redefining where the target is placed using a normalized geometric target.
Instead of blindly chasing the EMA self-teacher and falling into that mode-seeking trap, OPSD geometrically interpolates between two distinct policies.
Okay, what are the two policies?
The first is the self-teacher, which holds all the rich, verified context and token-level feedback.
And the second?
The second is a frozen reference policy. This is typically just the initial base model from before the optimization even started.
Wait, I need to stop you there because, well, if I'm looking at how standard PPO or GRPO works today, we already use the base model as a reference, right?
You're talking about the KL penalty.
Yeah, we calculate a KL penalty against the base model and subtract it from the reward to stop the policy from drifting into gibberish. Are you saying OPSD just swaps out the math formula on that penalty? Because that doesn't sound like a fundamental breakthrough.
That is the most common misunderstanding, and it's a crucial distinction. In standard RLVR algorithms, the KL penalty is additive on the final objective.
Oh, so it acts as a retroactive punishment.
Exactly. The model takes a step, the algorithm calculates how far it moved from the base model, and if it moved too far, it applies a scalar penalty to the loss.
And SROPSD doesn't do that.
No, SROPSD does not do that. The interpolation coefficient, which the paper denotes as alpha, directly shapes the underlying target distribution at the token level before any gradient projection even happens.
Wow, okay. So it's not a penalty at the end of the pipeline. It's changing the shape of the target itself at the source.
Yes. It is a log linear interpolation. If you set alpha to 1, your target is 100% the self-teacher, and you suffer from mode collapse.
And if you set alpha to 0, your target is 100% the frozen reference model, and you learn literally nothing.
Right. But by setting alpha somewhere in between, the paper often uses 0.90, you are creating an entirely new normalized target distribution.
This mathematically anchors the evolving teacher to the foundational knowledge of the original model.
You are preventing the target from drifting into a mode-seeking collapse before you even begin calculating how to move the student.
Okay, so step 1 is placing the target intelligently, anchoring it so the laser pointer isn't just spinning wildly. But placing the target isn't enough, is it?
No, it's not.
Because I had to read the ablation study in this paper twice. The results were so counterintuitive to me.
You mean about projecting towards the target?
Yeah, they found that if you create this beautifully anchored self-referenced target, but you project the student toward it using standard forward KL or Jensen-Shannon divergence, it actually degrades performance.
The empirical drop is significant. When they added self-referencing to standard Jensen-Shannon divergence, the model's performance on a sino-evil physics benchmark dropped from 79.4 down to 77.2.
So anchoring the target actively hurt the optimization process.
Because standard divergence metrics are too rigid. This forces the introduction of the second structural innovation, which is the Rényi Projection geometry.
We need to unpack what Rényi divergence is doing that standard KL is completely missing.
So Rényi divergence is a broader family of divergences controlled by a single parameter called the Rényi order, denoted as rho.
Okay.
As rho approaches 1, the formula mathematically recovers the standard KL limit. But the optimization magic happens when rho is set between 0 and 1.
What happens in that fractional regime?
In that regime, Rényi divergence applies fractional powers to the teacher-to-student density ratios.
Let's translate applying fractional powers to density ratios for a second. Standard KL is notoriously hypersensitive to extreme probability ratios, right?
Extremely sensitive, yeah.
Like if the teacher assigns a token a probability of 0.99, and the student's current policy assigns that same token a probability of 0.01, the ratio is 99.
And in standard KL, you take the log of that, the gradient explodes, and the optimization takes a massive destabilizing step.
It's an all-or-nothing magnifying glass that basically burns a hole in the GPU when the density ratio spikes.
That extreme sensitivity forces the optimization to overreact, which destroys the very stability the anchored target was trying to create in the first place.
But when you apply a fractional power to that ratio, say setting a rho to 0.50, you are effectively taking the square root of that extreme ratio.
Exactly. You are compressing a spike of 99 down to roughly 10. You are power tempering the extremes.
I picture it exactly like an auto-darkening welding helmet.
Yeah.
The fractional power, rho, acts as the sensor in that helmet.
Oh, I like that.
It lets the normal light through the reasonable density ratios, so the model can see what it's doing and learn effectively.
Right.
But the second a blindingly extreme gradient flashes, the fractional power immediately compresses that spike, darkening the lens so the optimization landscape stays smooth and stable. The model takes a reasonable step instead of going blind.
That tempering mechanism is what makes SROPSD fundamentally work. When the authors paired the self-reference target with the rho-tempered Rényi projection, the performance on that same physics benchmark shot up to 81.1.
From 77.2, that's a huge jump.
Yeah. The authors mathematically prove, I think it's in propositions 3.2 and 3.3, that the Rényi order controls the sensitivity to these token-level density ratios without altering the unconstrained target distribution itself.
The synergy between the anchored target and the tempered projection is the secret sauce. You need both to survive self-distillation. Okay, so mathematically squashing extreme density ratios and anchoring targets makes perfect sense on a whiteboard. But if I'm an engineer burning thousands of dollars on compute, I need to know this doesn't just work in a vacuum. What happened when they actually trained massive models with this?
The empirical evaluation in this paper is really aggressive. They tested SR-OPSD across 3 notoriously difficult domains: scientific evaluation, mathematical reasoning, and code generation.
And they compared it against heavyweights like GRPO and SDPO, right?
Yes. Let's look at science first. They used the sino-evil benchmark, which tests undergraduate-level chemistry, physics, biology, and materials science. They initialized policies from Quen 3.8b and OMO 3.7b instruct.
And SR-OPSD consistently crushed the baselines. On Quen 3.8b, it outperformed the strongest competitors by massive margins across the board. But looking at the charts, the most critical finding for practitioners isn't just the final accuracy number.
No, it's the long budget stability.
Yes. If you look at the actor entropy graph in the paper, it highlights a major headache in LLM training. Policies routinely degrade if you train them for too many steps.
Right. The SDPO baseline, whether it uses Jensen-Shannon divergence or reverse KL peaks early, like around step 100, and after that, the accuracy falls off a cliff as training continues.
The model literally starts getting stupider the more compute you throw at it.
This is the entropy collapse we dissected earlier. The model becomes overly confident in a very narrow set of incorrect reasoning templates. It just stops exploring.
But the SR-OPSD curve goes up and stays up.
Exactly. By anchoring the target to the frozen reference model, it maintains stable, healthy actor entropy over hundreds of steps. It mathematically prevents the rule collapse.
Meaning you don't have to perfectly time your early stopping to avoid destroying your model, which is vital. I mean, you don't want your run collapsing at step 300 while you're asleep.
Totally.
Let's shift to math, because mathematical reasoning is widely considered the most brutal regime for these models. They tested on AE, HMMT, AMC, and Minerva.
Math is unforgiving. The reasoning trajectories are incredibly long, highly structured, and entirely interdependent.
A single incorrect token choice at step 2 of a proof completely invalidates the final answer 20 steps later.
Exactly. And what the authors discovered on these math benchmarks is frankly alarming. Standard KL-based OPSD and SDPO actually caused severe degradation of the base model.
The base Quinn 3 model was objectively worse at math after standard self-distillation.
Yes.
Just imagine fine-tuning a model to make it a math expert, and it forgets how to do basic algebra because the moving target pulled it into a blind spot.
It's a nightmare scenario, but SR-OPSD completely reversed this degradation. On the HMMT25 benchmark, it boosted pass accuracy by 10 full points over GRPO.
10 points, that's massive.
Across all 5 math benchmarks, SR-OPSD achieved the strongest overall performance. It proved that you can successfully absorb dense, token-level feedback from ground truth solutions while preserving and even enhancing the foundational capabilities of the base model.
And that dense token-level feedback proves its worth even more in the code generation results.
Oh, definitely.
They evaluated scaling behavior on live Codebench v6 using Quinn 3 models ranging from 0.6 billion up to 8 billion parameters.
Yeah.
And the method scales beautifully.
It nearly doubled the base model success rate on the tiny 0.6b model, and it consistently beat both GRPO and SDPO at the 1.7b, 4b, and 8b scales.
The coding benchmarks validate the fundamental premise of why we need on-policy distillation in the first place, right? Code generation relies heavily on execution errors as feedback.
Yes. To fix a failed unit test, the model must locate the exact line of code that caused the failure.
But if you get a sequence-level scalar reward from GRPO that just says, -1, your code failed to compile, the model doesn't know if the bug was in the import statement, the logic of the for loop, or just a missing bracket at the end.
Right, whereas SR-OPSD provides dense token-by-token credit assignment, allowing the model to pinpoint exactly where its logic diverged from the correct path.
So to ground these abstract benchmark numbers, the paper provides qualitative examples of token generation failures.
And these are super interesting. They dissect exactly how the baseline models fail compared to SR-OPSD.
It gives practitioners a clear view of what mode-seeking behavior actually looks like when a model is generating text. For ML engineers dealing with LLM hallucinations in production, these aren't just academic curiosities.
No, these are exactly the infuriating, hard-to-debug behaviors that happen when a model optimizes too aggressively.
Take the physics prompt on nuclear decay.
Yeah, the prompt describes an element emitting 1 alpha particle and 2 beta particles and asks the model to calculate the change in atomic number.
And the SDPO baseline model literally overwrites the foundational laws of physics. It confidently claims that alpha emission decreases the atomic number by 1 instead of 2.
That is textbook rule collapse. The mode-seeking math amplified a slight initial error. The model became highly confident in that error, and it erased a fundamental fact from its weights.
While SR-OPZ, because it anchors to the foundational reference model, stays perfectly faithful to the correct physical laws.
The chemistry example highlights a different failure mode, though. The prompt asks for the calculation of the molar weight of a complex peptide molecule.
And the SDPO model starts out fine, right? It begins summing the atomic weights.
But mid-sentence, it just abandons the math. It outputs a generic, irrelevant template stating that the functional groups indicate a hydrophilic molecule.
This perfectly illustrates the danger of reverse KL. I mean, calculating molar weights requires exploring high-entropy token spaces, lots of specific numbers, addition, multiplication.
It's risky for the model.
Right. Spitting out a memorized textbook phrase about hydrophilic molecules is a low-entropy, easy path. The mode-seeking math practically trained the model to take the lazy way out to minimize divergence.
Whereas SR-OPSD's anchor forces the model to stay in the high-entropy math space and actually finish the calculation.
The most frustrating failure mode they highlight, though, is in mathematical reasoning, something called answer drift.
Yeah, in one example, the baseline model perfectly executes the logic to calculate the final price of a discounted item with tax. It explicitly writes down $69.78.
Which happens to be option B in the multiple choice list.
Yes, but then inexplicably, the model writes answer D.
It's so weird. It executes the high entropy math perfectly and then just hallucinates the wrong multiple choice letter at the very end.
The internal representations lose alignment, but SR-OPSD maintains strict calculation answer alignment. It calculates $69.78 and confidently selects option B.
When you look at those token-level outputs, the necessity of the map becomes undeniable. Without the reference anchor, alpha, and the Rényi tempering, Rivero, the model just loses its mind in these highly specific, subtle ways.
Synthesizing all of this, Zuo-sun and the team have proven that feedback in self-distillation cannot simply be treated as an unconstrained imitation signal.
You can't just hand a model a rich trajectory and say, be more like this.
Exactly. The geometry of the target and the projection must be rigorously controlled.
Which leaves us with a really fascinating thought to mull over. In this paper, the researchers use fixed values for these parameters. They set the interpolation anchor alpha to 0.90 and the Rényi order rho to 0.95. But what if an AI system could dynamically adapt its target interpolation and Rényi order mid-training?
It opens up the possibility of self-healing optimization loops.
Just imagine a training run where the model constantly evaluates its own uncertainty or measures its own policy drift against the base model at runtime.
If the system detects that it's starting to suffer from rule collapse?
Right. If it senses its own hallucinations creeping in because it's taking the low entropy path, it could automatically lower alpha. It would dynamically tighten the anchor to the reference model to regain its sanity.
And if it hits a massive density spike that would normally cause a gradient explosion, it could automatically drop rho,
darkening that welding helmet to protect its weight.
Exactly. On-policy self-distillation could become entirely adaptive, adjusting its own geometry based on the complexity of the batch it's currently processing.
The mathematical foundation laid by OPSD makes that kind of dynamic control feasible. The laser pointer is officially unmounted from the robot's arm, and it has an auto-darkening helmet to boot.
That's a great way to put it.
Well, thank you all for joining us for this deep dive into the source material on AI paper slop. We'll see you next time.